Okay, welcome back everyone. We're going to continue talking about capacitance, and last time we derived the capacitance for a parallel plate and a charged sphere, and this time we're going to do it for a spherical capacitor, which is actually two concentric spheres, and then we'll do a cylindrical capacitor. Okay, so in real life you don't see this example very often, but a spherical capacitor would be an inner sphere of radius A, which contains charge, positive charge, surrounded by an outer sphere. Whoa, could we do that on center maybe? That's pretty good. An outer sphere of charge negative Q. Okay, so plus Q and minus Q, and this would have a radius of B. Okay, so that means that the electric field, which we draw in blue, would be going radially outward, and the Gaussian surface that we would draw for this would be a sphere, which is between A and B. So to very quickly run through our calculations here, first of all, we've drawn the picture, and our geometry again is spherical. So that means that when we apply Gauss's law, the integral of E dot dA is Q enclosed, which in this case is just plus Q over epsilon naught. So that means that the electric field is basically the same as in the last example. Okay, as long as we're between A and B, it's Q over 4 pi epsilon naught r squared if r is, so A is less than r is less than B. And remember that E is 0 everywhere else. Okay. And that's just from Gauss's law. Alright, so the voltage for this is a little bit trickier, but we can find the magnitude of the voltage by taking the negative integral from A to B of E dot dr, and that's going to give us basically Q over 4 pi epsilon naught times 1 over r evaluated, oh I can talk today, from A to B or B to A. Okay? And that's going to turn into essentially Q over 4 pi epsilon naught times, and don't forget our negative sign there, right? We'll have 1 over A minus 1 over B, which is going to turn into B minus A, and then AB and AB. So we'll have Q over 4 pi epsilon naught times B minus A over AB. So that is our expression for the potential difference. Okay, so that actually we did steps 4 and 5 together. That would be step 4, finding the field. And then this is step 5. Okay, step 6. The capacitance, therefore, would be Q over delta V, which would be Q divided by Q over 4 pi epsilon naught times B minus A over AB. And everything is going to flip up. So we're going to have 4 pi epsilon naught times the expression AB over B minus A. Okay. And one thing that you'll see is that this reduces to the expression that we had last time for a sphere. And the only difference is that if A was equal to 0, well, as A approaches 0, then it would turn into 4 pi epsilon naught B. Okay? So we can kind of think of it that way. Okay. One more example, and now we have a picture. Excuse me. Let's find the capacitance for a cylindrical capacitor. So in this, the field is in red, and we have an inner sphere, or cylinder rather, with a charge of plus Q, and an outer one with a charge of negative Q. Whoops. Didn't mean to go backwards. Okay, so here's step 1. Step 2 is we've identified that it is cylindrical geometry. Step 3 is applying Gauss's law. E dot dA is Q enclosed over epsilon naught, which is just in this case plus Q over epsilon naught. Okay, now our Gaussian surface, just for reference, is going to be a cylinder of radius r. And we're going to say that the inner cylinder, let's make this show up, inner cylinder has a radius of a, outer cylinder has a radius of b. That didn't work too well. Okay. Okay. So step 4 is solve for E. Okay. So E times 2 pi r L, where if we look at this sort of from the side, L is the length of the cylinder. That's going to be equal to Q over epsilon naught. So the electric field is going to be Q over 2 pi r L epsilon naught. Okay, now we calculate the voltage. So the change in potential is negative integral. Now we can only go from A to B because otherwise our field will be 0 of E dot dr. Now this one's a little bit trickier, okay, because we have a 1 over r for our field. So we're going to plug in our field, so integral from A to B of Q dr over 2 pi, 2 pi r L epsilon naught. And we're just going to rewrite that a little bit. We'll take out the Q and the 2 pi L epsilon naught. I think I need to restart my computer, that's why it's doing this. And then we have the integral from A to B of dr over r, which is the natural log. So we have negative Q over 2 pi L epsilon naught times natural log of r evaluated from A to B. And to make a long story short, we take the absolute value of that, and what we're going to get is essentially Q over 2 pi L epsilon naught times the natural log of B over A. Finally, to find the capacitance, running out of space, I'll get rid of this. Capacitance is Q over delta V. So that means that the capacitance, the Q's are going to cancel out and everything else is going to flip. So we're going to get 2 pi epsilon naught L over the natural log of B over A. And that's it. Okay, so hopefully you have a better understanding now of how to find the capacitance of various geometries. In many cases, you'll just know what it is from a table or previous experience, but this is the process that you go through to find it. Next time, we're going to start talking about what capacitors actually do in circuits and how to find the amount of electrical energy that they store. We'll see you then.